Projection is the process of representing the 3D object on the drawing sheet. There are different types of projection. Mainly two projection methods are used in modern technical drawings: isometric projection and orthographic projection. Let's study those in more detail. Let's start with the isometric projection. Don't get scared by the word isometric. Isometric projection is just a fancy word for a 3D representation of the object on a drawing. But let me correct myself. It's not actually 3D because it doesn't pop out of the drawing. It's still a 2D representation of the object, but it gives you the visualization of the object as if you were viewing it in a 3D model. Isometric projection was first introduced in the early 20th century and quickly gained popularity due to its simplicity and ease of use. It became standard practice in technical drawing and is still widely used today. Although it's not a must to have an isometric view on the drawing, almost all drawings contain an isometric view. And this is because it helps to visualize the part without having to do a lot of mental work by looking at the orthographic projection views. Even experienced engineers and people who work with technical drawings daily still grasp the first idea of the part by having a quick look at the isometric view. Now let's see how to create an isometric view. To create an isometric projection, a drafter starts by drawing a horizontal line and then drawing two lines at a 30-degree angle to the left and right of the horizontal line. These lines represent the x and y axes of the object's three-dimensional space. The drafter then draws a vertical line at a 90-degree angle from the horizontal line, representing the z-axis. The intersection of the three lines forms the isometric axis, which the drafter uses to draw the object. The object is drawn using a series of parallel lines that follow the isometric axis. These lines are spaced at equal distances to accurately represent the object's dimensions. The resulting drawing is a three-dimensional object represented in 2 dimensions. Although the isometric view is best for giving a quick visualization of the part, it lacks the ability to show important details. If you try to add dimensions to the ISO view, it quickly becomes crowded with information. Also, the angles and circular elements are distorted. So, although it is helpful and recommended for every drawing to have an isometric view, it is generally only used for visualization and is not sufficient to fully describe the part and needs to be complemented with orthographic views. Before we go in depth into understanding what orthographic projection is, we must understand that this is a very important topic of engineering drawing. In fact, this is the most fundamental concept in engineering drawing. You cannot read engineering drawings without understanding how orthographic projection works. With that being said, let's look at orthographic projection in detail. Here also, the word orthographic is just another fancy word for stating that this type of projection is created by representing every face of the object on a separate view. So instead of trying to represent an object in 3D or looking at it from an angle, we take the object that we want to draw and rotate it so that we are looking directly at one face of the object. Let's call the face that we're seeing now the front face. So now we see the front of the object, but because we're looking straight at the front, we don't see the features on the side of the object, and we don't see the features on the bottom or the top or the back of the object. Now let's draw what we see on this front face of the object on a separate view on the drawing, and we call it the front view. Now if we rotate the object 90 degrees to look at it from the side, now what we see is only the side face of the object. We don't see what happens in the front view or in the back view or in the bottom view, etc. Now we only see the side. So we draw what we see on a separate view on the drawing, and we call it the side view. So if we want to draw or to add more views, we just keep rotating the object and draw what we see. Now, if we do this for every face, we end up with 6 orthographic views. Now the big question is how to place these views on a drawing. Do we just put them randomly on the drawing sheet, or are there rules to how we place these views in relation to one another? And yes, you guessed it right, there are rules. And they are called first angle projection and third angle projection. There are 2 laws that define how the 6 orthographic views are related to each other: first angle projection and third angle projection. In both cases, the views are the same, but the position of the views with respect to each other differs. In third-angle projection, which is common in the US, the views are arranged such that the view one sees from their viewing position is placed on the same side as they view it from. For example, the plan view, also called top view, is seen from above, so it is placed above the front face because it is viewed from that direction. The right side view is placed on the right-hand side of the front view, while the left side view is placed to the left of the front view. The rear view is placed on the left of the left side view, but it could have also been placed to the right of the right side view. First angle projection is commonly used in Europe, Asia, and other parts of the world. In this projection method, the object being represented is placed in the first quadrant of a coordinate system, with the object located between the viewing plane and the observer. Think of it this way. You are standing in front of the part, and you take a picture of it with a Polaroid camera that instantly prints the picture. In first angle projection, you would throw this picture behind the part. In third angle projection, you would put this picture behind you. Now I have a question for you. If you are trying to read a technical drawing of a part, how would you know which projection rule is used? Well, you can find the answer to this question in the title block. If you remember the lecture of the title block, then you probably know that there is usually a symbol placed in the title block to indicate which projection method is used. This symbol is a drawing of a cone. We stand in front of the cone, so we take a picture of it. The view we see now is two concentric circles, and using the same analogy in first angle projection, you would throw this picture behind the part. In third angle projection, you would put this picture behind you. Let me ask you this question. If you have a part in one hand and the drawing of this part in the other hand, to understand how the part looks like, would you rather look at the part or the drawing? You would probably go for the part, and it makes sense. But what if the part had internal features that are not clearly visible from the outside, like a hole, for example? Well, in that case, the best option would be to cut the part in half so you could see inside it. While this approach is unpractical with the real part, technical drawing gives us this superpower. And it's called section views. A section view is created by cutting the feature in two halves and looking at the area that has been cut. Of course, in an imaginary sense, using an imaginary saw. This way, we can clearly see the internal features of the part and give them dimensions and tolerances. For a section view, you need two things: the section view itself and an indication on another view on the drawing indicating the path that the imaginary saw took to cut the part. This path is identified by thickened lines with arrows indicating the direction of the view, meaning which half of the part we will be looking at. The line is also labeled with a section identifier, such as section AA, section BB, etc. The section identifier is used to match the section view with the corresponding plan view. But wait, now we have a problem. After we cut the part by the imaginary saw and draw what we saw in the section view, how can we identify which features on the part were sawed and which features are not sawed, like an internal groove or a hole? And the solution for this problem is by using hatching. Remember our imaginary saw that was used to cut the part? Let's now imagine that this saw was dipped in paint before it cut the part. Now, the areas of the part that came in touch with the saw will be painted, while areas that had no material, like holes, will not have any paint. Now let's replace this paint with hatching lines, which are parallel lines to indicate where there is material that came in touch with the cutting section line. These lines are usually drawn at a 45-degree angle, although other angles can be used if necessary. For example, if we are cutting in an assembly, then the hatching must be different for each part to improve visibility. Changing the angle to 30, 60, or 45 degrees is often the preferred choice for many designers. So, in summary, hatching lines are used to differentiate the cut surfaces from the surrounding areas and to provide a clearer view of the object or component's internal features. This means that only areas that contain material and our imaginary saw had to cut through it will be hatched. Holes and hollow shapes will not be hatched. Before we end today's lecture about hatches and section views, there is one more thing we need to learn. Let's do that in a simple, practical example. Imagine you have a part that looks like that. and you have a top view of this part on a drawing. Now you want to show its internal features in a section view. But the problem is that not all the internal features on this part lie in the same plane. So instead of drawing two section views using two different cutting planes, you can use another type of section views. In this section, lines do not have to be straight lines. They can also be stepped in, which they include an offset. This is called an offset section view. This can be helpful if the important internal features that we want to show are not lying in the same plane.
Let's think for a moment about the main aim behind the use of technical drawings. We use technical drawings to describe parts. This description could be used for manufacturing or for quality control. It could also be used for cost calculation. In any case, to properly describe a part, not only that you will need to define the size of the part, but also you will need to define the positions and sizes of all the different features of the part as well. And this is basically what we call dimensioning a part. With that being said, let's now look at the different types of dimensions. One of the most common types of dimensions is linear dimension. A linear dimension is the distance between two lines. These two lines can be the edges of the part, for example, to describe the height, width, or length of the part. You could use a linear dimension to specify the position of a feature, for example, the position of a hole in the part. In this case, the linear dimension is going to be the distance between the one edge of the part and the center line of the hole. Another common type of dimensions is the diameter dimension. Like the diameter of a cylinder, for example, you could either place the diameter dimension on the view of the drawing, which shows the circular shape of the feature, or you can place it on the side view, where you see the cylinder as two lines. In any case, a diameter sign is necessary to put before the number specifying the dimension. But there's another way to dimension circular features, in which is to describe the radius of the feature instead of the diameter. In that case, this is a radial dimension, and it has to be noted with the letter R instead of the diameter sign. This is more commonly used when the circular feature is not a complete circle. For example, you have a fillet on the edges of the part. In that case, you only have part of the circle and not the complete circle. One other type of dimensions is the angular dimension. This type of dimension is used to specify the angle between two lines on the part. Again, these two lines can be two edges of the part, or they can be central lines of features. Then there are dimensions that are used to describe special features. For example, to describe threads or chamfers. In that case, there is a standard way of describing these features, but we will have a deeper look on these special dimensioning types later on in the course.